All right, these are the notes for Algebra 2, Section 7.1. We're looking at exponential growth functions. And the first thing we want to do is deal with a little bit of vocabulary. Now, an exponential function is a function that contains a variable in the exponent. Usually it will be a number raised to the x power. Oftentimes we'll have this form here. We have y equals a times b to the x power. Now let's take just a moment to look at this. You should be aware that this is a, right? And a has to be a number that's bigger than 0, right? So a has to be bigger than 0. And we are multiplying a times b to the x. So b has an exponent, a does not have an exponent. And the exponent is what's changing in our function. So it would be a times b to the first, a times b to the second, a times b to the third, so on and so forth. Exponential functions tend to rise very quickly because the exponent is changing. And we'll see exactly what that looks like in just a minute. Now, if a is a positive number, that is, if the number in front here that we're multiplying by is positive, and b is bigger than 1, so if b is 2 or 3 or even 1.5 or 1.25, then the function is an exponential growth function. That means that whatever the function is, it's going to be growing, getting bigger exponentially. That is, very, very quickly. Exponential is a high-tech mathematical term that means very, very quickly. That's the old joke anyway. B, whatever b happens to be, remember it does need to be greater than 1 here, is the growth factor. So when we refer to the growth factor, we're talking about b, the number that has the exponent. Okay, so let's look at how this works. Now, when we're dealing with the parent function, which would be y equals b to the x, where b is any number bigger than 1, right? So b has to be bigger than 1. The parent function, the parent function would look like this. Now you can see the base in this case is b. Whatever b happens to be, that's referred to as the base. So the shape that we get is kind of this curvy line. And a couple of things are happening here. One, when the exponent is 0, of course, y is 1, because anything raised to the 0th power is 1. So we have a point at 0, 1. We also have a point at 1b, whatever b is. So if b was 2, we would have a point at 1, 2. And again, we'll see how this works when we actually start graphing these. But these are general characteristics of exponential functions. Now, one thing that is different is the way the graph moves. Now, it rises from left to right. That is, as we move from left to right, the graph is going very, 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 very quickly upwards. And the further we get to the right, the further we get in this direction, the faster it moves. Okay? Now, on the other side, we're moving to the left, but we're doing it in an odd way. And the way that we're doing this is the function will never ever hit what's called an asymptote, right? And for the parent function, the x-axis is an asymptote. And the asymptote is a line that a graph approaches more and more closely. Usually it will not cross the asymptote. In fact, everything we're going to deal with, the function will never cross, never touch the asymptote. So in this case, since the asymptote is the x-axis, and it even is nice enough to tell us, the graph will never touch the x-axis. That means that the domain of this function is all real numbers, because we are moving left and right forever. But the range is only y is greater than 0. Y can't be 0 because that's where that asymptote is. and all the values are above that, so y is greater than 0. Okay, so here we go. We get into the meat of this thing. We want to graph this function. We have 1/4 times 6 to the x. All right, so we're going to graph y equals 1/4 times 6 to the x. So we can see here 1/4, that's a. 6, that's b, which is also our growth factor. And x, of course, is our variable. So our variable is in the exponent. This is an exponential function. A is 1/4, b is 6. Since a is positive and b is bigger than 1, this is an exponential growth function. Now, in order to graph this, there are a number of ways we could do this by hand, but we're going to skip all that because these functions are a little bit tricky, given the values that they kind of throw at you. So we're just going to jump straight to the calculator. And here's how we're going to do this. We're going to go to our calculators. We're going to go to y equals. And we're going to type in our function. Now our function is 1/4 times 6 to the x. So on our calculator we do 1/4 and we do it in parentheses. Fractions should always be in parentheses. So we do 1/4 times 6, and we want to do to the x power, so we use the caret button to create an exponent, and we put x in the exponent. So 1/4 times 6 to the x. Now if we were to graph this, there's what our graph would look like. Now that's nice and all, and I will take a picture of that for our notes here. But that is not really going to help me. Okay, I can't really get much information out of that picture. Okay, so instead, I want to go to the table, and to get to the table, of course, I hit second graph, and you can see it gives me this list. Now, what you might immediately notice is that we have some really ridiculous numbers going on here. You see, when we get to the negatives, we start looking at really, really crazy decimals. And when we get to the positives, we start looking at really, really big numbers really quickly. So the only graphing we can really do is going to be right around 0. Right? Even -1 is a little bit too crazy. 0 is 1/4, 1 is 1.5, 2 is 9, and we'll see what we can do with those numbers. So I'm going to take a picture of this so I can have this for a reference, because these are the values I'm interested in. Make that a little bit bigger for my own reference here. Now, I want to plot some points. When x is 0, y is 1/4, so I'm going to eyeball that one about 1/4. When x is 1, y is about 1.5, so 1.5, I'm going to eyeball that. When x is 2, y is 9th, and I can't really graph that, right? There's 1, 2, 3, 4, 5. 9th would be way up here. So you can see that the graph already starts to go a little bit crazy. So instead, what I'm going to do is try and figure out where my asymptote is and then graph it from here. And it's going to be a little bit more of a sketch than an actual graph, but that's okay. Now, to figure out where the asymptote is actually pretty easy. As you can see, when I start going negative, my numbers are becoming bigger and bigger decimals. They're actually becoming smaller and smaller numbers. Right? This is 28 zeros and then a 9. So that's really, really, really tiny. So these are all very, very, very tiny numbers. That means we're getting closer to 0, which tells me that my asymptote is at 0. So the way I'm going to do this is I'm just going to start drawing this line close to 0 and then have it curve up and rise upwards. The only points I'm really having it go through are this 1.5 and this 1/4. And those are the only 2 points that I'm really interested in right now. And there's my graph. Now we're going to do the same thing over here. We're going to graph y equals 2 times 3 to the x minus 2 minus 2. Now this looks crazy. This is a lot of numbers. Fortunately, again, we have our calculator which can do the heavy lifting for us. So on our calculators, we're going to clear this out. We're going to type in 2 times 3 to the x minus 2 minus 2. 2 times 3 to the, now notice x minus 2 is in parentheses, is in the exponent. So in my exponents, I have to put x minus 2. I move the cursor to the right to get out of there. 2 times 3 to the x minus 2 minus 2. Now I'm going to, again, I could graph this. Doesn't give me any really useful information, although it does show me that it looks like it's leveling out here at -2. So that gives me an idea that my asymptote is at -2. But I do want exact points. So I go to my table, and here we are. Now, of course, again, my numbers get really crazy really quickly. So again, I'm really only going to be able to do stuff with the numbers around 0 or 1. Now, when x equals 2, and I'm just going to, again, make another copy of this, just for my own reference on my screen. Make it nice and big. Now, when x is 0, we're close to -2. So, you know, just 4, I'm just going to put a point there, real close. Probably even closer than that, really, if you want to get back right down to it. When x is 1, x is at, or y is at -1 1/3. So -1 1/3 would be about right here. Again, I'm just sort of eyeballing these. When x is 2, y is 0. So that's nice. I can put a point right at 2, 0. And I can put a point right at 3, 4. I can do that point as well. Now I know my asymptote is about at -2, or is at -2. So I can draw something that looks vaguely like an exponential function, and it's a little wonky, but that's okay. Now, there's my graph. I've plotted a few points. This one here, this one there. Those are the easy ones. I sort of eyeballed this one and this one, just to kind of give it a little bit more completeness. I'm being asked to state the domain and range. Well, the domain, as we know, are the x values. And the domain for all exponential functions is all real numbers. The range of all exponential growth functions, all the functions we're looking at today, are all going to be y is greater than the asymptote. And the asymptote here is at -2. That's that little imaginary line that we can't cross. So my range is y is greater than -2.